Okay, take a look at the high specific heat of water and take a look at how this does minimize that temperature fluctuation to, to within the limits that permit life. So think about the effect of the specific heat of water and what that does to the air mass and the temperature around that air mass while at it. So the picture that I'm going to show you, this is Southern California. Take a look. The Pacific Ocean is currently at 68 degrees. This is Fahrenheit, of course. So look at the cities that are around this. So Santa Barbara at 73, Los Angeles 75, San Diego at 72. Now the other thing I'm going to do is I'm going to show you a picture of the temperatures in Hawaii, and we'll be looking at the fluctuation of those as well. And the small land mass is completely surrounded by water. But take a look not only at the daytime temperatures, but we'll also look at day and night. And maybe I'll also show you one of San Diego. San Diego has such little fluctuation between day and night, and it's because they're on the ocean, and so that high specific heat of the ocean makes it so we don't see such changes in temperature. Now, as you go inland, take a look. San Bernardino, in this case, we're currently, it's at 100 degrees Celsius. Palm Springs up to 106. This is not uncommon. Once you move away from that water mass, you start to see these fluctuations. So anyway, that's what we talk about when we talk about the temperature fluctuations due to the influence of the water. Okay, now evaporative cooling, the next one. Evaporation is transformation of a substance from a liquid to gas. You probably learned that in chemistry or even physical science. The heat evaporation is the heat of a liquid must absorb. The heat of vaporization is the heat a liquid must absorb for 1 gram to be converted to a gas. Heat of vaporization. As a liquid evaporates, it remains. Let's try this again. Yeah, Dad's recording everything because he's doing a lecture, okay? Just recording everything because I'm doing a lecture. Evaporative cooling. Evaporation is the transformation of a substance from liquid to gas. So we have heat of vaporization. This is the heat a liquid must absorb for 1 gram to be converted to a gas. Now, as a liquid evaporates, its remaining surface cools. This is the process called evaporative cooling. Evaporative cooling of water helps stabilize temperatures in organisms and of bodies of water because that surface does cool down as it evaporates. Okay. So now, let's get to the floating of ice on liquid water. Ice floats in liquid water because the hydrogen bonds of the ice are more ordered, making the ice less dense. So in other words, you got these water molecules, those hydrogen bonds forming between them, spread them all out as far as they can get from each other. So we've got a hydrogen bond between each one, and I'll find a picture to show you this. But when it comes to cooling of water, we take our container of water and we start cooling it, and you know as things cool, they become more and more dense. Well, same thing with water. Water reaches its greatest density at 4 degrees Celsius. That's when the molecules are really packed together. But once you start hitting 3, 2, 1, the hydrogen bonds, the way they want to form, start to spread those water molecules apart. So, that's why ice floats on liquid water. Think about if ice sank. All bodies of water would eventually freeze solid, making life impossible on Earth. But also think about what would happen to the organisms below that ice layer as it started to sink. So, that's one of those hypotheticals for you. Okay. Water, the solvent of life. A solution is a liquid that is a homogeneous mixture of substances. So then we have a solvent. The solvent is the dissolving agent. Water is a fantastic solvent. The solute is the substance that's being dissolved. So I always think of like salt dissolving in water. Salt would be the solute. Solvent, the solvent there is the water. So then an aqueous solution is the one in which water is the solvent. So that gives you solution, solvent, solute, and aqueous solution. So 4 terms to add to your list of terms. Water is a versatile solvent due to its polarity, which allows it to form hydrogen bonds easily. Now, if you don't know this, likes dissolve like. So if you want to dissolve a polar molecule, you use a polar solvent. So that's why we can take sugar and dissolve it in water. But let's try it the other way. Let's take sugar and try to dissolve it in, say, vegetable oil. Vegetable oil is a non-polar liquid. So try that one on your own time sometime. And let's see what happens. Now, when an ionic compound is dissolved in water, each ion is surrounded by a sphere of water molecules, and this is called a hydration shell. And I've got a picture for you to see a hydration shell. And like always, we always show a lot of chlorine and sodium in this class. So, water can also dissolve compounds made of non-ionic polar molecules. So even larger polar molecules such as proteins can be dissolved in water if they have ionic and polar regions. That can still happen. Okay, so, and I may or may not show you an example. Yeah, I'll probably show you an example of that. Okay. Hydrophilic and hydrophobic substances. Okay, I like this because we're on water through all this. So, turn the light up a little bit there. A hydrophobic substance is one that has an affinity for water, so it's water-loving, hydrophilic. I don't know if I said that right. Let's try this again. A hydrophilic substance is one that has an affinity for water, so it's water-loving. A hydrophobic substance is one that does not have an affinity for water, so it becomes water-hating, phobia. Oil molecules are very hydrophobic because they're relatively non-polar bonds. Now, when it comes to a colloid, we haven't mentioned that one before, but a colloid is a stable suspension of fine particles in a liquid. Now, I can give you other examples of colloid, but the easiest one is whole milk. Okay, you got different sized particles, and they are suspended because of the size of their particles, but they're a colloid. Okay. Now, solute concentration aqueous solutions, the title of the next section of your reading. So, most biological reactions will occur in water. Now, the chemical reactions depend on the collisions of molecules, and therefore the concentration of the solutes in the aqueous solution. More solutes, more collisions, more chemical reactions. It's pretty straightforward. Now, this section, or this part of the book goes into some chemistry again, but it's all chemistry of water. So molecular mass, we had this before, is the sum of all masses of all atoms in a molecule. We had molecular masses before. The numbers of molecules are usually measured in moles, where 1 mole is equal to 6.02 times 10 to the 23rd molecules. That's a big number. Write it out sometime. Avogadro's number and the unit of Daltons were defined such that 6.02 times 10 to the 23rd Daltons equal 1 gram. And finally, we have molarity. Molarity is the number of moles per solute, molarity is the number of moles of solute per liter of solution. So that is our molarity. And in this class, we deal with some molarity of different substances, mainly acids and bases. Okay, new topic. Possible evolution of life on other planets with water. Now, these remarkable properties of water support life on Earth in many ways. So we have astrobiologists that are constantly seeking life on other planets, and they're concentrating their searches on planets with water because water is so important to us. Now, to date, there are more than 200 planets that have been found outside of our solar system. Matter of fact, I think that number's well over that. That's a published number in your book. But 1 or 2 of them contain water. And so we'll continue to look for planets with water. In our solar system, we believe that Mars has been found to have water. So that's the direction that astrobiologists are looking. Okay, and that ends concept 3.2. And, well, that ends the introduction, concept 3.1, and concepts 3.2. And I apologize for the length of my video.